So this is tutorial 2, week 3, and our quiz will be until this tutorial. Okay, so which means this one is also covered. So what we have learned in last tutorial is, so for specific coordination number, so there's a critical and the minimal chi-i and i-i ratio, so for which this contact can be maintained. So we already calculated one in the class and also calculated one in the tutorial. Okay, so you know that how it will be related with this RC over RA. Okay. Okay, then follow the steps. So there's altogether 6 steps. So remember the step 4 is the most important one. And also the coordinate and densification. So coordinate is root 2, densification is root 1. So both will happen. So that's what we learned this week. So how can we control to make root 1 happen more or root 2 happen more or whatever. So depend on your requirement. Okay, so and also we learn Young substitution and the Kelvin equation. So Young substitution and Kelvin equation so tells you how atom moves, because atom is going to move from the convex to the flat to the concave. Okay, so let's continue. So this is the one you should be very familiar with already. Okay, so let's derive this vacancy concentration together as in the handout. How long is tutorial? My tutorial is about less than half an hour. Okay. Derive the vacancy concentration equations as shown in handouts. Okay, so there are vacancies equals to this one. So first of all, so let's review what we have learned in the class. Okay, last Friday. So we said the particle pressure of a material above curved surface. Okay, so basically, so this is Kelvin equation, right? We have already seen, okay, in 2 weeks ago. So this is a Kelvin equation. But as a material scientist, we really don't like this norm. So how can we get rid of this norm? So there's a condition here. So the condition is P curve is very close to P flat, and we already know that this is a very valid assumptions. Okay, so as a material scientist, when you do any calculations, there's so many different assumptions, but we have to make sure the assumptions is valid. Okay, so then once we have these two together, so we can get rid of this norm. How can we do so? So we said we have to use these mathematical equations. Norm 1 plus x equals to x minus x squared over 2, x cubed over 3, x power 4 over 4. Okay, so this one is a universal one. So it doesn't matter this x is equals to what. You can always use these equations. Okay, the thing is, now if my x is very close to 0, if x is very close to 0, then we can have an approximation here, which means these equations can be simplified. For example, I've already showed you, right? So if this one is 0.1, right? So which means the first term is 0.1, but the second term will be 0.55, 0.005. Right? So this will be even smaller, 0.0033. Okay, so you can see this higher order, all this requires higher order will become smaller and smaller and smaller. So compare with this first one. So it is too small. So we can make it negligible. Okay, so that is why, so always remember there's a condition here. So if the x is very close to 0, okay, so then this norm 1 plus x simply is just this first one. All the rest can simply just take away, right? So norm 1 plus x equals to x. Okay, so now I'm asking one question here. So if x is very close to 0, again, same condition. Okay, so what is exponential x equals to? If x is very close to 0. So what is exponential x equals to? Very approximate. Okay, yes, okay, so you can see if I put exponential here, okay, so then this is exponential x, right? But this side, exponential norm actually can cancel each other out. So exactly, so it's supposed to be 1 plus x. Of course, if x is very close to 0, this one is also very close to 1. Both answers are correct, but we need the equations. So equation is still this 1 plus x. 1 plus x. Very good. Well done. Okay. So this is something extra. So later we're going to use this conclusion also. Okay. So let's continue, okay? So we already know that 1 plus x are equals to x, okay? So if, okay, and also if we know this x is very close to 0, so 1 plus x then is going to be very close to 1, right? So if we know a is very close to b, so which means this one is also equals to a over b, right? If a is very close to b, right? So 1 plus x equals to 1 and also is equals to a minus b, because this one is also close to 1, right? Because this one is also close to 1. Okay, then if we just make this one just open up, so you can, because you need 1 something here, right? Because you also need to come up the 1 here. So 1 plus b, a minus b, correct? So all these are linked together, okay? 1 plus x, if x is very close to 0, then if a is very close to b, so a over b is also equals to b, and also this one is going to equals to 1 plus a minus b over b. So you just do this, make it out. Okay, so continue. Okay, so then we know that norm a plus a over b equals to a minus b plus 1, right? Because these two are equals to each other. So then we also know this a minus b over b, if a is very close to b, is going to be very close to 0, right? So which means these two actually are the same. Same thing, okay? It's x, okay? 1 plus a minus b is actually x here, because both x and both a minus b over b is equals to 0, okay? So then we can also take this one as x, so norm a over b is going to equals to a minus b over b, okay? So that is the all this derivation here. So if we continue, since we put this one as a, this one as a b. Okay, so then because we know these are close to each other, a is close to b, right? So then we can just take out a minus b here. So which means you have a delta p here. Delta p here, okay? So which is p curve minus p flat equals to this one, p curve minus p flat. Okay, so we can get rid of this norm now. Okay, so that is a lovely part. So then all the rest, so it's very straightforward for you to come up by yourself. Okay, so this is the first one. So now let's move to the second one. Okay, so the second one, okay, so first of all, signal here. Signal here. Now I'm asking you, this signal refers to the Wilkinson concentration of the, is with a shape. This shape have some radius, yes or no? Have some curvature, yes or no? Signal means you have curvature or no curvature. Every time if you see no, which means there's no curvature there. Okay, so which means there's no like R here. Okay, so so this one requires equilibrium, which means you don't have any shape constraint. So why we talk about shape all the time? Because syntony is about what? Syntony is always about two particles with a radius. When they come together, how atom moves, right? Okay, so this signal is equals to K prime exponential. This is enthalpy of formation, and KT. All these are constant. Everywhere is constant. All these are constant. Okay, so this one is without shape. So now I'm asking you. So if I have a convex now, which means something like this, a convex now. So if I want to create a vacancy here, okay. So do you think I need overcome higher NH, more NH, or less NH compared with a flat one? Can you type the answer here? Okay, for this signal, this enthalpy of formation, which is the one which is a flat one, which means you don't have any shape, any constraint, okay? But now, if on this surface of a curvature there, if I want to get rid of this atom to become a vacancy, so do you need overcome extra NH or less NH to become a vacancy? Okay. Yeah, more NH, exactly. More NH to become a vacancy, correct. Okay, so like for example, now I put a curvature now. So for curvature, things so you have to put a delta mu here, because that's what we say here. You need overcome this extra NH to become vacancies. Okay, so you need a plus a delta mu here. Am I correct? Okay, so then you can do the mass manipulation here. Okay, so since you have a plus here, so then you equals to K prime exponential, you take out one portion and also times exponential, okay, delta mu over KT. Okay, so these two can just speed out like this. Okay, so now I'm asking you, so you already know that delta mu is Young's substitution is 2 omega gamma over R, right? So what is this one? Can you type? What is this portion? K prime exponential. What is this one? 瞬间, 锐阶. So this one is simply just a signal, right? Signal. So this is just signal here. Okay, so the signal, this one is simply equals to signal. Okay, so then we put this delta mu replaced with the Young's equation and Kevin equation here. Okay, so in the end, we will have signal exponential minus 2 omega gamma RKT. Okay, so this is the C curve. Okay, so condition, every time we say exponential, we want to get rid of. How can we get rid of? So there's a condition. So the condition says for most part, actually this is a valid, it's a very valid assumption. So then this one, actually inside one, is actually very close to 0 because omega gamma over R is much smaller than KT. Okay, so all these are most are constant. So once you put all these value in, then we'll see most of them are constant, and this is also a valid assumption that I will be very close to 0. Okay, so which means what you have seen here is very close to 0. You see something 0, right? You were happy already, right? You can always go back to the equation we have done it before. So norm 1 plus x equals to x, right? If x is very close to 0. So now you have an exponential here. So just now we have already done, I think Reggie have already solved these equations. So if I put both exponential here, so then this one cancel each other out. So actually norm exponential x is going to equals to 1 plus x. Okay, so that's what we see here. 1 plus x is equals to exponential x. 1 plus x equals to exponential x. If I put exponential on both sides, okay. So this is so, then you're very happy. So which means now this one is a bit messy. So I just discard and rewrite, okay. So obviously now, since as I said, I put exponential here. Okay, so then this one is exponential x equals to 1 plus x. So which means this one now, x, this is also the x. Okay, so let's continue. So in the end, so this is the equal thing, it's the same thing. So we use it, so C curve, so this one, C curve is going to equals to C norm. So then we can get rid of this norm, this exponential, 1 minus 2 omega gamma RKT. Okay, so this is the derivation of these questions. Okay, you can see this is just the same equation. You just do all sorts of variations, then you will get your conclusions. Okay, so this is just a very common and standard material scientist tricks to get rid of norm, get rid of exponential, and it's a very commonly used if you are doing PhD or some more simulation work. Okay. So just share with you. So this is a first question, okay? And let's continue. Okay, summarize migration paths of particles and vacancies, as this will be fundamentals. So this one is so important because it is very important for you to understand the centrings, okay? So migration paths of the particles and vacancies, okay? So this one is the one we derived together in the class, and this is the one we just derived in the tutorial question 1. Correct, right? So it's pretty straightforward. You know that since you have changed the sign, one is positive, one is negative. Since you change the sign, so now you know, to recap, the pressure over the convex higher than the concave, which is mountain have the highest pressure and the valley have the lowest pressure. But the vacancy is the other way. The vacancy is the valley have the higher vacancy concentration and the mountain have the less vacancy concentration. Okay, so they're the opposite. Okay, so then it's very simple for us to calculate this equation, to answer these questions. Okay, so atom move from the convex to flat to concave. Vacancy move from concave to flat to convex. Okay, so it's a very, very straightforward one. So, but I really want you, so after many years, you may not remember, I'm sure you won't remember all these equations, all these derivations, but I'm very sure you will remember this graph. Okay, I want you learn all this more or less like common sense for material scientists. Okay, so atoms move from the mountain to the valley. The vacancy is the opposite way, and the atom is just like a human being because we are solid, right? We are solid one, we are not empty one. Okay, so we are the one as the atoms. Okay, so continue. So this is a very important concept of material science, and also it's the fundamentals in sinterings. Okay. So explain which two paths give densification in the solid state sintering. So remember, so in the first part, we mentioned there's a root 1 and root 2. So the difference between root 1 and root 2 is there's a very huge difference is in root 1. If you want densification, so make sure your grain boundary densify first. Am I correct? Followed by what? Followed by densification. Followed by what? Can you type? So root 1 is always you have the grain boundary densify first, followed by the 生阶, Vijay, who else? Vijay? Yeah, followed by the green growth. Excellent, green growth. Thank you, Vijay. Yeah, green growth. Okay, excellent. Okay, remember that one. So, okay, so now we said, so we have 5 atomic mechanisms. So 1, 2, 3. Okay, so 1, 2, 3 is very simple. You can see 1, 2, 3, what happened in 1. So basically, so atom condensed from the vapor. So because you heat up, you always have atom evaporated, right? So the atoms condense to what? To which place? They always go to where? So you can see the destination of all the atoms actually are all, destination of the atom are all what? Shenjie, Yuja, what's your opinion? The destination of the atoms goes to, everything goes to where? Goes to this place, this neck, okay? Okay, so the first P1, which is condensed and to stay in the in this valley, and also the surface diffusion. Also, the second one is atom move from the surface, all the way to the valley, and also same thing here, but it's through below the under the surface. That one we call it a volume diffusion. Volume diffusion, because we said before. So A place it is a convex, and the B place is a flat, okay, and the C place here, it is a concave, okay, concave, okay. So let's continue, okay. So that's what we put here for the P1, P2, P3 is all these surface particles move to the neck area. So you can imagine they only move to the neck area, but they have nothing to do with the grain boundaries, right? So this one, only when you have anything to do with the grain boundaries, you will have densifications. So for these three, P1, P2, P3 does not allow the atom move closer. There's no densification, only cross length. Okay, so P1 is evaporation condensation, P2 surface diffusion, P3 is lattice diffusion from surface to the neck. Okay, so this one row in the neck size, no densifications. This is constantly. Okay, but as I said, the most important thing, this one is so important. I remember, okay? All these things make sure happen at all this grain boundary first. This is the first one, okay? So the densification at the grain boundary, then quickly and only grain goes later. Okay? The pores get smaller and disappear with a time. But the thing is, this is a P1. Where's my mouse? Okay, P1, 2, and 3. will only cause this crossening, okay, but it's P4 and P5. So why is P4 and P5? So let's continue up, okay? So this is P4 and P5. So first of all, it happens at green boundary already, right? So as we, according to the root 1, root 2, so continue up, okay? So there's a different ways, either it's along the green boundaries, not the green boundary, or below the green boundaries, but again, doesn't matter, all goes to the neck. Go everywhere, go to the neck, okay, P4 and P5, okay, and there's this, okay, first of all, to fulfill the first condition. The first condition is unless you have atoms move along the green boundaries. So the next condition is if you want densification, so as we have already seen in this illustration, so we have to make sure so that when there's vacancies come, so in the end, what is densification? So densification means what? Densification means your vacancies is going to be filled with atoms. Okay, so that's densification. You need to get rid of the vacancies. You need to get rid of the pores. Okay, so if you can make sure they come opposite way, so then you will make this one happen, as we have already seen in these illustrations. Okay, as I thought this one is easier for you to understand. Okay, so let's continue. Okay, so that's what we say here. So you can see, so you have a vacancy moving one direction and atom moving the other direction. So then in the end, so you will just fill this, get rid of these pores, get rid of these vacancies. Okay, so that's what we put here. Materials in the green boundaries or the region between the powder particles. Okay, green boundary is just where the powders in contact first, right? They're supposed to swap the atoms at this region, okay, at this region, green boundaries, okay? So then you're going to move, the atom move to the neck pore region. Neck is equals to pore region, okay? So let's continue, okay? So then we fulfill the first condition is let's happen at the green boundary. So the second condition is you have to make sure the move in the opposite way. So as we already explained in the class, so where we have the higher vacancy concentration, so I think you have already answered this one in the class. So maybe I just ask you one question here. So which one have the higher vacancy concentration? Is the neck or the green boundary? Then I know you understand or not, or remember or not. Which one have higher vacancy concentration? Which one? Is the neck or the green boundary? Excellent, excellent. Thank you, Senja. Okay, excellent. So yes, it's a neck or green boundary. Actually, it is the neck. Neck have the higher vacancy concentration. So which means your vacancy move from the neck to the green boundary. Am I correct? But atom is the opposite way. Atom move from the green boundary to the neck. Okay, so then you have this opposite flow. So second condition also has been met. Okay, so that's why you will see the atoms, because they move opposite way, so they are going to become densified. So that's what we put here. So P4 and P5 give densifications. So first of all, there must be materials replacement from the green boundaries to the neck and the pore regions. Okay, so this is number one. So because according to root 1, I make sure the green boundary densified first. Okay, then atomically, we also have learned this Young-Substance equation, the Kelvin equation, and we have derived so many equations there. All these equations tell you that it is true that the atom vacancies is going to move oppositely, because in P4 and P5, atom move from the green boundary to the neck, and the vacancy move from the neck to the green boundaries. So this is the second condition. It is also has been fulfilled. So which means these two add up together, let you P4 and P5 to have these densifications. Okay, so yesterday one student sent me email and he actually summarized very well already. Okay, so there's two conditions. Condition 1, make sure everything happens at the green boundary, because that's the first initial starting contact point between the two particles. Okay, secondly, can you make sure there's opposite flow, and it is true atomically from this Young-Substance equation and the Kelvin equations. Okay. That's Q3. Okay, so let's see Q4. So explain why liquid sintering will lead to faster densification compared with solid phase sintering. Okay, so what is liquid phase? I'll help you review. We learned this last Friday, right? So you can see you have an A here. The rest are B. Okay, so if it's solid, which means you only have B, right? You don't have A, but it's liquid. So this liquid, which means you have this A, which is used as a liquid later. Maybe because it have a lower melting point, so at a certain temperature, it become a liquid already. Okay, so and also, so that's what we hear, the composition of starting solid are such as to result in the formation of a liquid phase. So you can see you have a liquid phase, which means now this one changed to gamma, okay, because this is L. This is L, okay? Liquid in between. And this liquid phase, so as we said before, if it's a solid phase, right? If it's a solid state centering, you have particle 1 and a particle 2. So you can see all of them actually in contacting with vapor. So in between, they actually have gamma SV. Okay, gamma SV. But once you have a liquid in between, so you change the interface. So this interface changed to gamma LV, liquid vapor. Gamma LV, okay, which is this one, liquid and vapor, okay? So how can we say whether it is a theta angle? Okay, how can we say it's a wetting or non-wetting? I think because according to the question I asked, many of you already understand, but just recap here. So theta is less than 90 degrees, it means it's wetting. If it's larger than 90 degrees, which means non-wetting. Okay, so this is one way. So theta angle. You can see, you can check the theta angle. So there's another way is you can see if this liquid love this solid, this is solid, right? Love the solid. So they will try to spread as much as they can, right? Spread. But if this liquid does not like the solid, they were trying to curl up. Okay, so for example, like you can see the interface is much less compared with the wetting, right? So this is one way you can to see whether it's a wetting or non-wetting case. Okay, because sometimes students might have problems to find where is the theta angle. So the extreme case, right, for this one is a theta is equals to what? Tell me, can you type? Theta equals to? In this case, theta is actually equals to 180. So this is completely, you can say, obviously this liquid definitely does not like the solid because you can see none of this place has been get wet. Okay, the contacting point, contact only have one point here. Okay, so this is definitely very long wetting case. Okay, use extreme for you to understand. So there's a very important concept here is once you make sure it is a wetting case, then you will have something magic we call it a gamma LV. This gamma LV, there's a name for this one, equals to the capillarity force. This is capillarity force. So now let's see how this capillarity force works. So let's continue, okay? So we said this is wetting case and this is non-wetting case. So wetting and non-wetting. So for example, let's see this a non-wetting case first. You have a particle A and particle B, right? So again, quick review what we learned now, okay? So this case, theta is actually larger than 90 degrees, right? Okay, 90 degrees, okay? So now I'm asking you, so this is sorry, 1, sorry, 2, okay? And in between is liquid, right? Between is liquid, okay? Once you have shape already, right? Because now you have a curvature now. Okay, so in this case, now I'm asking you PC and P naught, what is the relationship between here? So if in theta larger than 90 degrees, so PC is larger or P naught is larger. Which one is larger? Can you type? Which one is larger? So we said if this one, let's say if something like this, or something like this, something like this. So PC, P naught, PC, PC, and P naught. Okay, so you can say now I have different interface. So if this one, obviously the first case, right, PC is equals to P naught, right, because it's a flat one, so you won't have any curvature. Okay, but if something like this, that is, okay, so obviously the PC is actually larger than P naught, right? Otherwise you won't have such curvature, right? And for this case, P naught is actually larger than the PC. So you can cause this curvature. So this is another way for you to understand, okay? So obviously in this theta larger than 90 degrees, so obviously this PC, this case, okay? So PC is actually larger than P naught. Okay, so that is for the theta is larger than 90 degrees. So obviously if PC is even larger than outside, which means they're going to pull away these two particles, correct, right? So you can see that's why. So these two particles actually is pulled away. So that's what we see. Where's my mouse? It's here. Okay, so you can see it's pulled away. Okay, so that's a non-wetting case, but in sintering, we want what? In sintering, the most important thing is let's just quickly make them come together fast. Okay, so that is not, definitely not theta is larger than 90 degrees. Okay, so we have to use this case when theta is less than 90 degrees. So theta is here, less than 90 degrees. Less than 90 degrees. And also we have again PC and P0. So obviously in this case, you can see P0 is actually larger than PC, right? Actually in mass, we call this one is a sidal form, this sidal shape, inside this sidal shape. And in this case, we say this actually the R, if you use mass, you will know that R is a negative thing because it's a concave case, concave. So it's a negative. And also the other thing, easier one for you is PC and P0. In this case, P0 is bigger. P0 is bigger, right? So that is why in this case, okay, so it's a attraction. So there's an attraction. So there's a large attraction force for these two to bring in together. So that is the what we say here, the capillary force, which is gamma LV, can give rise to strong attractive force between the particles. So when combining with lubricating liquid, this is lead to very rapid and magnificent particle rearrangement and densifications. Okay, so that is the capillary force. It's very much wanted if you want bring the particle to come in closer fast enough. Okay, so that is question. Okay, explain why liquid phase will lead to faster densification because of these impurities. Some student knows it's a sintering 8. Some book called the sintering 8 means help the sintering happen faster. Okay, sintering which appear as a liquid phase first during heating up, right? Okay, if the liquid is wetting the particles, so which theta is less than 90 degrees, there will be a large capillary force induced to quickly bring the particle closer, enhancing densifications. So therefore, it will lead to faster densification. So that is this portion. Okay, so remember this is conditions. Conditions are wetting, have to be wetting. There's another one we briefly talk about it in the lecture. Is actually there's another way, and also it helps a little bit. Is meanwhile during the liquid phase sintering, normally atoms move much faster in liquid than in vapor. This could also further enhance the sintering rate. So what does this mean? So for example, okay, I give students always this graph so they will understand it very easily. Okay, so for example, this is milk powder. So in order A is full of glass or water and B is just air. So for example, if I want my milk powder atoms when I pour in, so it move from this position 1 to position 2. Position 1 to position 2. Okay, so which one is going to occur faster, A or B? Can you type? Which is easier? Which is faster? For milk powder to move from 1 to 2. So A is easier or B is easier? So obviously, right, because this is a liquid, so the atom actually is going to move faster here compared with in the vapor. Okay, so now if we say, so it's a solid state sintering and liquid phase sintering, so solid. So actually the atom movement is through the vapor. So there's a vapor here, right? But once it becomes liquid phase, so in between you have very thin layer of liquid, okay? So the atoms actually will move much faster in liquid. So that's why we said, okay, so during liquid phase sintering, normally atoms move much faster in liquid than in vapor. So this could also further enhance the sintering rate. Okay, so we said these two reasons add up together to make sure the liquid phase sintering happen much faster than the solid phase sinterings. Okay, number 1, there's a capillary force. So number 2, so the diffusivity, as some people call it diffusivity. Okay, so diffusivity or the atom move much faster in liquid than in vapor. Okay, so this is question 4. Okay, so let's continue. So, and also help to review, this is important. So what are the 4 conditions you have to meet, okay, in order to have densifications? The first one we explained already, right? the wetting of the solid phase by liquid is needed. First of all, you have to make sure it's wetting. If it's not wetting, so actually you pull things away. Okay, and also appreciable solubility of the solid in liquid to transfer materials. So what does this mean? So why you need a certain solubility of solid in liquid to transfer materials? Because what is sintering? Sintering in the end, you still need to make sure your atom can move, right? Now, for example, if we go back to this one, if I change in this B now, if I pour some like oil inside, it's not water, okay? Because we know that milk powder does not really dissolve in the oil, right? So it will be also difficult for this oil, for this milk powder to move through the oil. Am I correct? So that is also a condition for the sintering, liquid sintering. So it's better you have appreciable solubility of the solid in liquid. Otherwise, you won't have the atom movement. Okay, it's also easy to understand that, right? Make sure you have a good solubility of the solid in liquid to transfer the materials. Okay, and for the second one, the final solid phase. Final solid phase, which means when you are smaller, because we didn't learn the equations, okay, because when I is smaller, which means your capillary force, actually this gamma LV is again inversely proportional to R, but doesn't matter since you haven't done it. So please just remember, if you have a smaller solid phase, so this LV, gamma LV, the capillary force will actually be larger. Once it's larger, so this capillary force will bring the particle to come in much faster. Okay, so this is a second one. Okay, and the last one is also simple, right? Sufficient, which means now you have so many particles everywhere. You cannot just make these two wetted, but this one you don't have enough. So obviously it won't help, right? So it's better you have everywhere can be wet the solid phase sintering. Okay, a sufficient amount of liquid to wet the solid phase. Okay, so this is the 4 conditions. Please remember it, and it's also essential for rapid classifications. If you prefer high creep resistance, so do you prefer liquid phase or solid phase? So as we said, as a material scientist, you always know that there's no perfect solutions. Once you bring something good, you also have something bad. Okay, so you have to balance. So for example, we already said in liquid phase sintering, you must have a liquid. You must have something to become liquid first. Am I correct? Which means you need a sintering aid. So no matter what, this sintering aid, it is a no matter what, it is impurities, right? You have to, these impurities need to have a low melting temperature than the host, than the mother materials. Am I correct? Okay, so then in the end, where will this impurity go? Because you can imagine heat up, so become liquid first, no matter what. When you cool down, even this liquid and these impurities will become solidified, right? And will go to where? So most likely all these impurities will go to, or the sintering aid will go to the, can you type? It's just 2 words. 瑜伽, 瞬间. The impurities will always go to the green boundary. Okay, green boundary. Okay, so you have to be very careful here. Okay, so first let's see these tables. We know that if you need high strengths, make sure your microstructures has small grain size, uniform microstructures, and floor free. Okay, floor free. Most floor we always refer as a pores because most of the time we don't want pores. Okay, so this is high strength, high toughness, because we haven't explained about toughness that much yet. So I'm going to explain next week. Okay, so forget about this one first. Okay, then there's a high creep resistance. So if you want your material have very high creep resistance, make sure you have large grains and free of amorphous grain boundaries. Actually, almost all the green boundaries, it is nearly amorphous already, right? Because this is somewhere very disordered already. But you can imagine now you add some foreigners in. So this synchrone A is a foreigner. So it's going to make this green boundary even more disordered. More disordered, which means it will be more amorphous, more to the amorphous side, okay? So that's the problem for the creep resistance. They're very, very sensitive to these green boundaries impurities, okay? So better not use it, okay? And also we said the optical transparency. So for example, if you want a material very optical transparent, what you can do, first of all, get rid of the pores. So because the pores is going to scatter the light. Okay, so this is number one. The other one is the grains can be either much smaller or much larger than the wavelength of the light. So wavelength of the light, okay, so you know the visible light is 380 to 780 nanometer, right? So you have this range, okay, 380 to 780, okay? So then this 2R is going to, this is a range, so which means your grain size is either much bigger than this one or much smaller than this one, this range, okay? So this will also help to make your grains become more, make your materials become more transparent. And also the low dielectric loss. So you can see they prefer small and uniform grains, okay? And the only difference here is the catalyst. So the catalyst, you need large, very large surface area. So very large surface area equals to what? Every time if you saw something like, oh, I need a very large surface area for my applications, so you will immediately know that it's going to relate to what? Can you type? 位阶, 如节, sorry, 位阶. 身价? What's your opinion here? Okay, so every time if I said, oh, I want my material have very large surface area, make sure it is very porous. Okay, so this is a very important concept as a material scientist. Okay, so you have to find a way to make it super porous. Okay, so that is the catalytic applications. So let's continue. Okay, so that's what we said. The good thing is liquid phase sintering is more forgiving in terms of powder packing, more rapid, hence more economical than the solid state because you have a liquid phase there. So it's going to make everything happen faster and lower temperature. Okay, so we give you one example, like for example, for silicon nitride. Silicon nitride is a very high melting temperature ceramics. So if without the liquid phase, so it won't even densify. So this is a good thing. So it will help you to become densified much faster. Okay, but okay, so always there's a but. Anything there's always a but. Okay, however, in many applications they don't want this green boundaries, the heated, the gassy film. Gassy means very amorphous. There's a green boundaries. For example, the creep. Okay, and also the second one is ionic conducting glass phase. Because if you want insulator, they're very, very sensitive to this green boundary. If the green boundary it is very conducting, so it will influence the insulation properties. Okay, so that's why what we say here in today's electro ceramics, liquid phase and the residual porosities are trying to avoid it. Okay, these are the two examples I gave to you. Okay, creep resistance can be significantly compromised by presence of a glassy phase, the gas phase at the grain boundaries. Okay, this one because it's going to soften upon the heating, and therefore we can only choose solid sinterings. So that is Q5. Okay, so we are very quickly can summarize already. Okay, so for this week, we already know that vacancy move opposite to the atoms. Vacancy move from valley to land to mountain. So last week we learned the atom moved the other way. So this week we confirm that vacancy move to the opposite way. Okay, and also we said, so densification, for densification to happen, you need two conditions. So the first condition, make sure it happen at the green boundary, right? Green boundary area. Okay, so second one is make sure there's opposite flow of vacancies and atoms. So in P4 and P5, so number one, the atom move from the green boundary to left, while vacancy move from the left to the green boundaries. Okay, so this is P4 and P5. And also in liquid phase, we know that large hydroreactive force due to this liquid phase. So we're bringing the solid particle much closer. It comes in these densifications. Okay, and also different applications need different morphology, therefore different processing is needed. Okay, so that's number 4. And also let's quickly summarize what we learned. Okay, sintering driven force are reduced surface energy or Kosling root 1 and root 2 are Kosling and densification. And Young's substitution tells you atom move this way and we can move the opposite. Okay, 5 atomic mechanisms are evaporating P1, P2, P3. So these 3 contributing to Kosling. Okay, and we know that P4 and P5 green boundary and bulk diffusion along this green boundary contributing to this densification. Okay, so atom of course have to move from green boundary to net, and because they move from net to green boundary. And also some general marks. So in general, because green boundary need to be higher temperature, right? So that's why. So if you want higher densification, make sure you have high enough temperatures. And also if you high densification, make sure you have a good green density uniformity, and also there's not much agglomerations. And impurities, certain impurities can suppress Kosling and green growth and lower the green boundary mobilities. Okay, again, it's trying to make sure the green boundary densify first instead of green growth become. Okay, green growth need to happen later if you want densification. And also there's a large particle distribution will promote abnormal growth. So it's very straightforward. If you want something uniform, you start with something uniform. Okay, add uniform, start uniform. Okay, very easy logic here. And also in liquid phase, so we said a large capital force by wetting liquid will attract the particle closer. So this is going to enhance the densification. So we said there's a 3 stage, the particle rearrangement stage, which just a liquid bring them in, and the solution reprecipitation, and also the skeleton sintering. Okay, these are 3 stages in liquid phase sinterings. Okay, and 4 conditions need to be met. So you have we have reviewed this one. And also in many applications, this one can be very harmful. So we talk about 2 examples. So one is a creep, the other one is insulators. Okay, and the last one, which is the property, is very much dependent on the microstructures. So which means you have to design where I use a good process to get a good control of your microstructures in order to get the properties you wanted. Okay, so that is all for this week. So tomorrow, 5 p.m., same link. Use the same link. So we have a very quick math tutorials. So just review number 1, number 2, trying to narrow down what is examinable in say 2. Okay, thank you very much. I stop recording first.